So this is what we left off in the last video. This was part A of the question we were looking at in terms of ionization energy and electron configurations. So part B is asking, explain why the increase between the 6th and 7th values is greater than the increase between the 5th and 6th values. So again, this is a question about ionization energy and electron configuration. So maybe we can use something we've already created or base some of our calculations on what we already have. So we're talking about the 5th and 6th, and the 6th and 7th, and we're trying to show why the increase between the 6th and 7th values is greater than that of the 5th and 6th values. So we can't use the ionization energy of the 9th and the 10th values. So let's get rid of some stuff first. So let's erase all of this. Since it's not very relevant to our question. Okay. And again, something we can start with, a good starting point typically is starting by writing an equation. So we know 5 to 6 and 6 to 7, right? So 5 to 6 is just going to be Al5 plus goes to Al6 plus an electron, and Al6 plus yields Al7 plus an electron. So again, let's try to draw the new configurations. So Al5 plus is removing 5 electrons. 1, 2, 3, 4, 5. 1s2, 2s2, 2p4, and and then we have Al6 plus, right? So we always want to look at the starting point. We don't want to look at the ending point. We want to look at the starting point so we can identify the electron being removed. So we have a 1s2, 2s2, 2p, so we're removing 6, so we're going to remove one more, so 2p3. And now what we want to do is we actually want to rewrite this based on some of the information we know about orbitals. So we know this is going to be a 1s2, we have 2s2, and then we know that the p sublevel actually has 3 different types. There's going to be the x, y, and the z. Now we can actually draw this out if you wanted to. It's going to be something like this would be the x, and then there's going to be this, which is going to be the z, and this is going to be the y. So what we can actually do is we can label these specifically. So we know there's going to be the 2px, right? And we're going to have 2 of them. Then we have the 2py. We'll have 1 of them. And then to have 4 in total, we'll have the 2pz, and we'll have 1 of those. So we could basically put 1 in each if we have a 2p3, and then we have to double up on 1. So we can double up on the x one first. So now we can do the same for this, right? We basically have, for the Al6 plus, we have 1s2, 2s2, 2px1, 2py1, and then a 2pz1, right? So if we draw the orbital diagram, right, we have the 1s, the 2s, and then we have like something like the p sublevel, right? We have 3 orbitals in the p sublevel. So we have this, following Pauli exclusion principle and Hund's rule. So for this, for the Al6 plus, we have the 1s, we have the 2s, same thing, except for the 2p, we only have 1 electron in each one. Let's make this a bit more legible. So what we have is we have 1 electron in each orbital. So clearly this is the most crucial differentiating element between the Al5 plus and the Al6 plus electron configuration. So what does it mean when there's two electrons in the same orbital? Well, they have opposite charges, meaning that there's going to be repulsion. There's going to be a repelling force. So when you're removing an electron, when there's a repelling force, it actually helps sort of push the electron out of the orbital, and it makes it more easily liberated. It decreases the ionization energy. It makes the ionization energy less. So that's why when we're removing an electron from the Al5 plus to produce the Al6 plus, it requires less ionization energy because there's going to be a repulsion here. While we have a half-filled orbital, there's no repulsion. So there's no repelling force to help the removal of the electron, which explains why the ionization energy for 6 to 7, the ionization energy when removing an electron from the sixth ionization number is going to be much, much higher. So the ionization is going to go up, 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 up for this reaction right over here. And that actually answers our question. The increase between the 6th and 7th values is very, very significant. There's a lot of energy required to remove or liberate one electron because there is no repelling force that's present within the filled orbital in the p sublevel, the 2p sublevel. And that's going to be it for this video.